Here you can see an overview of the optical bench and the equipment, as well as the instruments that we used in the MINOAS project demonstrators. The bench belongs to the Telecom Lab of the Department of Electrical and Computer Engineering of Aristotle University of Thessaloniki. Line-of-sight experiments with free space optical signals are presented in the first demonstrator. Here, you can see the system block diagram of the first demonstrator, accompanied by the optical path schematics and photos of the testbed. For more information, you can refer to deliverable D6.1. The audio track is heard played through RXPC speakers. Here, you can see the two USRPs that are used. Next, you can see the continuous wave laser source, Santec. The black SMA coax cable brings the data from the TX USRP into the Mach-Zehnder interferometer RF port. The Mach-Zehnder interferometer modulator output SMF cable is connected to the collimator lens. Blocking the beam by hand muffles the song, only noise is heard. The SLM is configured as a flat mirror, slightly rotated. The fiber coupling lens assembly focuses received light into the SMF. Received light is amplified in an EDFA, notice the characteristic green-lit EDF spool. EDFA output is guided to two filters, to reduce ASE noise. The filtered light is guided to the photodiode. The photodiode output is the RF signal, guided by the blue coax cable to the RX USRP. The laptop processes the signal and sends audio to speakers. The audio track is heard played through RXPC speakers. We close up on the screen of the laptop connected to RX USRP. Here you can see the continuous wave laser source. We close up on the Mach-Zehnder interferometric amplitude modulator. Here you can see the collimator lens and the Pyrex mirrors. The top Pyrex mirror is used. Blocking the beam by hand muffles the song. Only noise is heard. We close up on the RX fiber coupling lens assembly and on the SLM. The SLM is configured as mirror. Received light is amplified in an EDFA. Notice the characteristic green-lit EDF spool. We close up on the filters used to limit the ASE EDFA noise. We close up on the photodiode receiver. We close up on the screen of the PC connected to the TX USRP. In the third experiment, we employ QPSK. We can see the computer controlling the RX USRP. We close up on the measured bit error rate, which is 0. This was expected due to the clean constellation graph. The beam is blocked by a hand, which collapses the constellation. A hand is seen momentarily blocking the beam, right after the TX collimator lens, and, in the background, the screen of the RX USRP shows the QPSK constellation collapsing and instantly recovering. Next, we observe how the constellation changes for different levels of received power. In -7 dBm. In -4 dBm. In 0 dBm. In 3 dBm. In 6 dBm. In 9 dBm. In 12 dBm. In 13 dBm. The laser is off. Finally, we present the second and the third demonstrators, which refer to non-line-of-sight beam splitting and beam steering, respectively. Here, we observe the system block diagram, accompanied by beam path schematics, and the characterization setup. We can see the continuous wave setup at the two optical receivers. Laser is on, but both OPMs show 0 received power because the SLM is set it off. The camera is placed at the POV of the SLM. The TX collimator lens can be seen in the background. Now, in the controlling PC, we set SLM equals linear grading. Notice that both OPMs receive approximately equal power, which verifies the beam splitting functionality. Then, we set SLM equals blazed grading, so that the phase profile, white to black, is left to right. The OPM1 power is greater than the OPM2 power. Next, we horizontally flip the blazed pattern. Now, the OPM2 receives higher power compared to OPM1. When we reset SLM to off, both OPMs receive 0 power.